Hey, first I want to lead you guys down the path of what we have already done. Because one of the things that I like about this class is that everything basically falls in order of how to do a statistical report, whether you're going to do a medical report or a financial report or all these different things. It falls in order. So I want to guide you through what we've already done in the first steps. So we first started this year with an experiment. Okay, we talked about let's design an experiment so we can collect data. Whether we do that with an experiment or an observational study, we want to collect data so that there is no bias and so that we have a representative sample. Okay, so that's the important part. After you collect your data, let's talk about how to describe it or display it. You need to first decide, do I have categorical things like red, blue, yellow, orange, that does not average? Or do I have numerical data that it makes sense to average it? And then I'll display it in things such as histograms, box plots, stem and leaf plots, all those kinds of things, okay? Collected data, displayed data. We also talked about their measures of center and spread. What are the two primary measures of center that we have focused on? Mean and median. Very good. Mean and median. I will tell you right now that mean is the one that we will focus most of the year on, okay? But sometimes that's dangerous, and we'll talk about that in a second. As far as measures of spread, what measure of spread coincides with the mean? If I'm talking about the mean of something, good. Then the spread I would describe is the standard deviation, okay? And for median, if I had a box plot, what measure of spread would I describe with that? IQR. Very good. Now, I want to use mean and standard deviation, but there are some times when I would not. When would I be cautious of using mean and standard deviation? If my data had skews or outliers. Very good. Because I know that mean is pulled, what? In the direction of the skew. Very good. All right. So, we collected data, we displayed data. Then, we've recently talked about how to handle it when it is two variables, say time and distance or whatever, and how could I make predictions? If I have a representation of how to make a prediction, I have an equation for the prediction, then where does my actual data stand in relationship to that prediction line? How far away is it? What is its residual? Furthermore, if I have an equation that is not linear, how do I flatten it? Is it an exponential model? Is it a power model? To flatten it so that I can find a good fit to make proper predictions. Okay. All that has led down this path to what we are doing today. And starting, this is chapters 14 through 17, and we're going to talk about probability so that we can identify what should be happening. What's the chance and the likelihood that something should happen? And then we will say, okay, my data that I got, how does that compare to what should have been happening? All right, that's where we are headed. We're going to be interested in comparing what actually happened to what I hypothesized should be happening, and then next semester we'll do a test to reject the hypothesis or not reject it. So that's where we are headed. See, it all connects. So the first thing I want to talk to you about is this language of probability in two specific words. By the way, what you have picked up is the notes, which I actually want you to more just listen here at the beginning. So I didn't want you to write, take time and be distracted writing things down and take that time of writing it down. It's just faster for me to tell you. So some of that's already written down for you so you guys can just listen. So here we go. So let's talk about flipping your coin, which you will be doing shortly, but don't do that yet. Okay, so when you flip your coin, would you expect the outcome of that event? Is that a random occurrence?
Tails never fails.
Tails never fails, so it's not random? Okay. Well, when you flip your coin, is the location that it'll land on actually supposed to be uncertain? If it's a fair coin? It is. When you flip that coin, you don't know before you flip it if it's going to land on a heads or a tails. So that is uncertain. The outcome is uncertain. That is randomness.
Or you can be certain that
You can be certain that it lands on heads or tails. That's true. Okay, that's true. That's different. So, but here's what happens. For these random events, if you performed these random events over and over and over again, then in the long run, a true probability falls out. In the case of the coin, what true probability will fall out if it's a fair coin? What's the probability of heads in the long run? 50%. Now, right away, it might not start that way, but in the long run, it's going to settle down to that true probability. And so, after a very long series of repetition, that true probability falls out. And we're going to experience that here with a little activity we're going to do in a second to demonstrate the law of large numbers. Okay, so that's a vocabulary term that you need to know. The law of large numbers is going to talk about what happens as you flip that coin many, many, many times. All right, so on your second to last page, you have got something that looks like this. Okay, so turn to your second to last page. You have two of these, and we are going to be talking about the probability of getting heads on your penny.
Zero.
Okay, let's talk about the probability of getting heads on your penny, on a penny. And this is going to be the cumulative, so up until that point, frequency. So I demonstrated for you on the top chart how your bottom chart's going to look once you start collecting your data. But I want you to look at the top chart and see if you can tell what I had. So I first flipped the coin, and based on what you see on the top chart, what did I get on my first flip of the coin? But you can tell based on the cumulative frequency, what did I get? How many heads did I get out of one trial? I got 0 heads out of one trial, so therefore I had gotten a tails. Okay, I flipped the coin again, and based on that picture, I have accumulated 0 heads out of 2 trials. So I'm still sitting at a cumulative frequency of 0. So the next one, I flipped the coin, and you can see based on the picture, I got what? I got a heads, because I have 1 heads out of 3. Look at the picture there at the top. I have 1 heads out of 3 trials. So I now have a cumulative frequency of 1/3. Okay. Now, based on that picture, I'm going to flip the coin. And based on that picture, what do I have on my coin? I have another heads because I have 2 successes out of 4 trials, which is up here at 50%. Okay, let's do one more. I'm going to flip the coin one more time. Where on that top part did I end up? I got a tails because the cumulative frequency is still 2 successes out of 5 trials, and that is 40%. So I want you to do your own on the graph below. You're going to do your own 20 trials and 20 flips and record those. You can get out your phone to do your little math on that. So I'm going to give you 4 minutes. Go. Your final, once you look at your final percent, final cumulative. So look at the number that you have in your last 20. And I want you to think in your brain right now if you fall into one of these categories. So we've got here right now. Okay, so our sample set is 20, so we have 24 people in our set. So I want to know, did anybody have 75% heads on their penny? 75. 70, any 70s? So we got two 70s, okay? 65%. How many 65% do we have? This is the end percentage, okay? 60%. So just two, okay? 55%, okay? Two. 50%. How many 50 percentages? Four. Wow. Okay. 45%. Okay. 40%. Okay. 40 is three. Okay. 35 is one. 30%. One. And 25%. Really? Okay, yeah. Okay, good. Now you say I need to add one here, and I need to add one here. Okay, I don't know if that totals up to the 24 that we have. I think there's probably a couple that did not raise their hands. But here's the idea. I would imagine that if I made a histogram of this, in fact, I should have made this. It looks a little skewed to the left. Oh, no, skewed right. Okay, look. I would have 5, 4, 3, and then 1, 1, 1. Okay, over here I'm going to have 2, 2, 1, 2, and 0. Okay, so that would be a very rough sketch of my histogram. That's nice. It's somewhat symmetric, not perfect. Okay, but somewhat symmetric. It's definitely unimodal, and it's centering here around the 50. Okay, so that's nice. Now, I want to tell you that 20 trials is in no way even close to the long run. So, while more of you were there at 50%, here is a better demonstration of what the long run is. In fact, this is a computer-generated simulation. You can see that at 20, this one is close to 75% on the heads of the coin. But look, it has been calculated, and I'm going to talk to you about this in a second. This was a computer generation. It's been calculated that it really takes until about 1,000 to be 95% confident that you're going to wind up between 47 and 53%. And so you do settle down to closer to the 50% as you get closer, as you get 1,000 and above. So if you flip a coin 1,000 times, I am 95% confident that your cumulative frequency is going to be between 47 and 53%. Yes. No. Okay, no, we're not going to do that.
Keep on flipping it some kind of way.
Okay. And that would not be considered random. If you have a technique to make it flip a particular way, then that's not random. It has to be done randomly. Okay, now, listen up. In my quest to explain stuff to you better, I found this little explanation about one thing that gets frequently confused. You do have this paragraph on the back of your little activity sheet that you just had. So let's talk about it. First of all, by definition, the law of large numbers is a theorem in statistics. Okay, so theorem meaning it can't ever be proven, but it is a theory that as the number of identically distributed, meaning same probability. So every time you flip the coin, if it's 50% chance every single time, okay? 50% chance every time. Randomly generated. See? Same thing. You cannot predict its outcome. As you do more and more of those trials, then your sample results, your experimental results, will approach the theoretical results. So the more trials you do, the closer you will get to what was expected, theoretically. Okay? Furthermore, we're not going to actually do that computation, but I want to talk to you about this thing called law of averages. That is, sometimes people refer to that when they talk about going to casinos and gambling. Okay, this thing called law of averages. Okay, let's talk about Herschel's information. He had what, 5 out of 20? Is that what you got? He had 5 out of 20 heads on his coin, so he only had a 25% success rate. Well, guess what? Yes, the law of large numbers says that as you put that coin a whole lot, it's going to settle down to what's expected at a half. All right. However, when people see this law of averages, they think, if you were gambling in a casino and you had, you were doing maybe red and blue or red and black on the roulette table, okay, which is another 50% thing. If you had that, then you might think, hey, you know what? I need to start betting the other way because I think either I'm on a hot streak and I need to keep betting because I'm going to keep getting black or whatever color it is. Okay, hold on a second. Or you may think, hey, you know what? It's supposed to average to 50-50, and I've only gotten 5 heads on the coin, so I bet you I'm due some tails because it's got to average out to 50%. That is called the law of averages, and the casinos expect that their people that go in there are betting on this law of averages, which means on average it's going to come out to the same thing. That implies that there is some mystical force that's going to somehow increase the probability of getting the heads because he's only gotten 5 so far. And so then, you're going to change, you're going to expect there to be a higher sense of heads that are happening on the coin. But the law of large numbers says no such mystical force exists. The probability of heads versus tails doesn't change just because you've only gotten 5 heads on the coin so far. So, it can take a very, very long time. In fact, what I just told you before, there's a 95% chance that it'll fall, 95% confidence interval, it'll fall between 47 and 53%. You would have to exceed 1,000 trials. That's math that we'll get into the second semester, so I don't expect you to understand how they came up with that, but there is formulas involved in that. So, a couple comments. First, over here, Tyler, what you got? Oh, the roulette wheel's not 50-50 because there's one free, so there's not the same number. Oh, there's one green. How about the black and, are they equal? Is there 101 spaces or whatever? Gotcha. Okay. All right, what else? Okay. So, in essence, think about this. I want to talk about the law of large numbers and how the law of large numbers keeps gambling casinos in business. How does the law of large numbers keep gambling casinos in business? Okay. Okay. We're gonna go beyond. No, we're talking straight pure numbers game. Why is house always winning? Okay, see, Byron says the house is always winning, and I want to know why that's the case. It's not always winning. In fact, have you ever seen Vegas Vacation where the sun goes out and he pulls a slot machine and he won a car? He pulls another one, he won a car. He pulls another one, he won a car. So he won 3 or 4 cars. Now, if that happens all the time, the casino's going to be way in debt. But what does the law of large numbers say? Go, Thomas, do you know? Okay. What's the law of large numbers telling us about these games and such? Over time, out of a large amount of time, the casino may be giving out much money today, but in the long run, over thousands and thousands of trials, the true probability will come out. So if they set a slot machine to be 25% of the time the person will win. They may pay out $100,000 today to a person, but in the long run, people will win only 25% of the time. Hey, did you know that they can do that with slot machines? They can calibrate it to what the true proportion of the wins is going to be. There you go. So, get this. When you go to casinos, yeah, there's this really neat show I've seen, and if we had time, it would be fun to watch it, but they have different ways that you can beat the slot machines, and they have, over time, people come up with these different ways to beat them, and then they fix it, and then they find a new way to beat it. But anyway, so when you go to a casino, they have all the slots kind of grouped together, and a lot of times they're in hotels, so everybody's walking through there, whether you're of age and playing or not. But anyway, so like this, on the outside edge of the slot machines, they calibrate those machines to have a higher probability of winning. Why do they do that?
More people can see.
More people can see the winning, have people winning. And then they want to go and be a winner too, and they'll go in there and do that. You're right. So, but in the long run, it will only come out to exactly what they calibrate that winning to be. Okay, so in this case, now Herschel, how many tails did you have in a row? Just 5?
Yeah.
Okay, he had 5 tails in a row. Anybody else have more heads or tails in a row than 5? What'd you have? 10. Woo!
Oh,
10.
Tails. Sorry.
How many
I
consecutive?
had 10.
Okay. Herschel had
I
10
was thinking
consecutive
heads.
tails in a
I
row.
had 9.
Okay. Now he did have 5. How many had a lot of heads on their coin in a row? What's the most?
5.
You had 5. Anybody else have a lot? You had 10 heads on that one. Okay. 10 heads on your coin in a row. So, question. What is the chance then of getting the heads or tails for the heads on the next flip if you've already had, in this case, 10 in a row?
50%.
It is still 50% chance because the next flip is independent of what you've just flipped, and it does not have a mystical force making it change and more likely. Okay, very good. I wanted to show you this one little thing. First of all, probability has to be a number between 0 and 1 because you're talking about your part that were successful out of the total trials that you have done. So it's always a portion. It's always a number between 0 and 1. Furthermore, you know that's always going to add up. All the different probabilities will add to 1. Okay, so these are things you know. You've done these in earlier probability stuff in grade school. And if you want to talk about the probability of something not occurring, then it'll be your 1 minus the probability of something occurring, okay, because it's the complement. And that takes us to this picture. You don't have this on the notes, but if this is the set of all possibilities, this is the probability of A landing in this section. If I say that this section is 35% of the data, then this little C right here notates the complement. That's the other portion that is not A. So the complement is the not A. So if the A is 35% of the data, then how much is the complement? 65%, because I know those total up to 1. Okay? Next, I want to do this actually with the class in here, and so I know that since Reed came in, we've got 25 people in here, and A is going to represent how many of you, the number of students that have blue eyes. B is going to represent the number of you that have brown eyes, and then we're going to see how many of you have blue eyes and brown eyes. Okay? Oh, sorry. Blue eyes and brown hair. Sorry, brown hair is what I meant to say. Okay, so let's get our number. Okay, so let's go ahead and talk about, this is really, it's not hard, but it's a notational thing. Let's talk about where to put these numbers. When you fill in your Venn diagram, I want you to always start where it's most restricted. In this case, has the most stipulations put upon it. So you have blue eyes and brown hair, and that would be 3 of the people in here. So I'm going to put 3 here. Now, this hexagon contains all of the blue-eyed people, and I am already accounting for 3 of the people. So if it is totaling 10, then what's left in just this gray section? 7, okay? See, that's a notational thing. So you know this entire thing is 10, of which 3 of them also have brown hair. Okay, so then that means over here for the brown-haired people, to total up to 14, this section, just brown hair and not blue eyes, is 11. Okay, so let's count then who has neither blue eyes nor brown hair. Okay, so that, who didn't raise their hand for either one of those? 1, 2, 3. You didn't raise your hand for either? Okay, 4. Did you? Okay, either. Well, let's see. Okay, y'all, let's see if we're good. Y'all got 4. Count this up. So this together, all of this union of blue eyes and brown hair together is how much? 14, 21. Hey, that's good. You guys did a good job. So neither, you guys, I had 4 people raise up. So this is 21 has union of blue eyes and brown hair, with 4 has neither nor. Okay, good. Now, a couple other notations. Let's talk about union versus intersection. This symbol here stands for union. Union you can think of as or. You don't have this on your paper except for it's already written on one of the pages, but you can write it somewhere if you want. But anyway, union is or, but I also want you to think of it as the union all together. So this is going to include the blue-eyed, the brown-haired, and the ones that have both are also included in this. So how many are A union B? Blue eyes union brown hair. All of this, which is 21. So all of that is the union. Okay, now, this is the intersection. It is more restrictive. It's where they intersect together. It's also called and I can remember it as and because this little symbol, you can easily make it an A. So it's blue eyes and brown hair, and that would be how many people? 3. So that's the 3 that we had in the middle only. It's just this section here. Blue eyes and brown hair. Okay, so that's union and intersection. So far we've done law of large numbers. We've filled in a Venn diagram. We've talked complement. We've talked union. We've talked intersection. We have one major concept left, and this is in your notes. So this is, I've added this year. I've not ever given this out in this way. This is a common vocabulary that is very confused. So you have a page just on the vocabulary, disjoint, and independent. So turn to your notes on that. Okay, so I'm trying to make this clearer because it's a commonly misunderstood vocabulary word. So here we go. Disjoint. Disjoint means that the events cannot occur at the same time. If you get the heads on one of the coins, then you cannot be getting the tails on that same flip. If I tell you that you got the heads on the coin flip, then you are not getting the tails on that. It's on the same coin flip. Okay? They cannot occur at the same time. If one of them is happening, then the other does not happen, guaranteed. So, there's a change of events, or a chain of events that's changing the probability of one of them happening, which makes the events not independent. So actually these last 2 sentences I'm going to demonstrate with this example here. So here we go. Pretend like I have a deck of cards here, and I want you to bet on if the card you pick is going to be red. You're going to be picking a card. I want you to think. You're going to pick a card, and the probability of it being red is going to be what? Well, okay, we'll take the jokers out. So just 52 cards. Okay, we got 52 cards. We have 4 suits. And the suits are diamonds, and hearts, which these are both red. And then we got our spades, and then the clubs, which are both black. How many are in each suit? How many in each suit? 13 in each suit. So that's in each suit. Okay. All right. So now you know the makeup of the deck. The probability of red is 1/2, because 2 suits are red out of 4. All right. But guess what? I'm going to peek at that card that you picked, and I'm going to give you a hint. It is a spade. So now, what does that do with your bet? Okay. So does that help you place your bet? Of course, because now you know the probability of it being red is 0. So you're going to bet against red because I told you it was a spade. So the probability changed because red and space are disjoint. They cannot happen at the same time. A picture of that would be this. The red would be here, and then the spades are over here, or maybe here's, I don't know. If we were to draw a picture and they were probably the red and the black, we've got spades and clubs and diamonds and hearts. So if it's a red, it's not a spade, it's not red. Okay. So disjointed events. But guess what? Here's the next thing. Since the probabilities changed, then by definition, they are not independent. Because, let's talk the word independent. Independent means that the events can occur at the same time. There can be overlap. If one of them happens, then it will not affect the other one happening. If I flip this coin, will it affect what I'm going to get on this other coin? The fact that you got 10 heads in a row on your coins, will that affect what you get on the next flip? No. Those are independent. The occurrence of one event has no information or no bearing on what's happening on the next event. So here's the card example with independence. So watch this. Pick a card. You're going to place a bet, whether it's red. You know it's 50-50 chance that it's red. But I'm going to give you a hint. The hint is that it's an ace. So if I say it's an ace, then now what are you thinking your probabilities is? It's still 1/2 because there are 4 aces and 2 are red and 2 are black. So I have not helped you at all by telling you it's an ace. Alright, so here is this. Watch. Do you see this line? This line here is a way of notating the word given that. So what this is saying is that the probability of red is 1/2. The probability of red, given that I tell you it's an ace, is still 1/2. So both of those are 1/2. Since me telling you it's an ace did not change the probability of it being red, then those are independent. Red and ace are independent events. Okay. Now, I'm going to see if I can quickly go through this. You have this all written out, so you don't need that. You can read through that. I want you to find the part that says final questions. It's on the back of the second page. And we're going to skip the first 2 and do this problem here. So here we go. First question, find the probability of B. What's the probability of B? 0.4. What's the probability of A union B? That's all together. A union B. 0.8. Okay. Is that class? Okay. We'll go over those last 2 tomorrow. You do have homework. You need to start. Yes, this is your homework here. And don't. The only way to get probability is to do it. So don't be going off of somebody else.
Right.